So this is the most important theorem in the entire class. I know, it's actually pretty great though, it's not like super hard. So it's called, there are two parts of the fundamental theorem of calculus. We're gonna do some today, we're gonna do some Monday, we'll do both parts today. So now that you know an integral means an area under a curve, we're gonna define a function where we find the area from a fixed point to a point that is changing. So the integral from a to b means the area from a to b, right? This thing means the area from 0 to x under some curve t. And so you use a different variable here, because if you didn't, whenever you replace this x by some number, you'd replace that by that number as well. But the point is you have some function, and you define this new function that finds the area from a number to a number that's changing. So like if I plug in x equals 1, that's the area from 0 to 1. If I plug in x equals 2, it's the area from 0 to 2. That's what it's telling you, okay? So let's find those values and then sketch a rough graph of what that g looks like. So we're going to find g of 0, and g of 0 means input 0 for x, right? So that's the integral from 0 to 0 underneath this f curve. And so what's that going to equal? 0. Because an integral from a number to itself is just 0, right?
I gotta throw them out there while I know them.
Okay, good. G of 1, I bet you can do that one too, is the integral from 0 to what number? 1. And so you find that by looking and saying, okay, well, the area under my curve from 0 to 1 is, I think it's a half, I think it's 1. I think it's 1/2 times 1 times 2. Do you agree? So I believe 1. Yes?
Oh, yeah.
Yeah? Okay. How about g of 2? That's going to be the area underneath the f curve from 0 to 2. That's going to be 3. Do you guys buy that? Okay. Now the next one, g of 3, is the integral from 0 to 3 f of t dt. And I think with this one, probably can't get it exactly. Do you agree with me? Because it's curvy, it looks kind of like parabola-ish. So, I think it's more than 1, right? Because if it was an area of 1, it would be that, right? So I don't know, 1.2 or something like that?
Take 6 sections of it.
Ish, whatever, it doesn't matter, but it's about 4.2. You're just gonna have to guesstimate that one. G of 4 is the area from 0 to 4.
When you say guesstimate it, but you use some sort of...
I know that the area here, if that was a triangle, is 1 because of the work I did to find the area from 0 to 1. And I know that the area of the whole box is 2. Does that make sense? I kind of figured that, that little bit that's missing, maybe 0.2-ish or something like that. Now, I claim for G of 4, you can actually find that one exactly.
Yeah, it's 3.
It's 3, and you can use the fact that this area and that area, they's going to cancel out, right? Because they're the exact same, except for one's positive and one's negative, right?
Right.
So that's going to be 3 again. And then G of 5 is the integral from 0 to 5 f of t dt. So that's going to add that in, which is actually going to be 3 minus 1.2. Does that make sense? So it'd be 1.8. Okay, and now let's use those points to plot G. So 1, 2, 3, 4, 5. Okay, with this g function, what do you get when you plug in 0? 0. What do you get when you plug in 1? 1. How about 2? 3. How about 3? 4.2. 4, you get 3. 5, you get 1.8. Sorry. Okay. It's a really not obvious relationship. But here's what I claim that I think you could believe. Could you believe that g prime of x equals f of x? Could you use a little bit of what you know about how to graph a derivative to buy that? So take this g graph. Yeah, okay, look at this g graph. When would the derivative of g be 0? It'd be 3, because the tangent line has a 0 slope there, right?
Oh.
And what from 0 to 3, the graph of g prime would be above the x-axis, right? And the specifics of why it looks like what it does, I didn't really account for, but you see, you could believe it as something like that, right? Well, now it's decreasing, right? So it's below, and the fact that it goes back up, I mean, I don't think that you have, the picture isn't a spectacular explanation of why this is true, but you can probably buy that there might be that kind of relationship there, right? It turns out that I have a limited time because there's just we're gonna run out of class time. This is what you can prove, and it's the first part of the fundamental theorem, that this g of x function that finds the areas, if you find g prime of x, which means you take the derivative of that thing, is just equal to f of x. I'm not going to have time to prove it, and the proof is pretty tedious and a little bit tricky, so it's just not going to happen today. But what this says, in some sense, is that this derivative undoes that integral. Okay, so somehow they cancel each other out, and seriously, all that changed is this f of t became an f of x. The variable inside changed and nothing else. Okay?
This logic, does that make g of x the antiderivative of f of x?
By this logic, g of x is an antiderivative of f of x, because g's derivative gives you f. Yep. Now there's a couple funky things that you have to kind of keep in mind, that the variable in this thing is in the power. What's inside this function doesn't really matter. You don't differentiate that. The thing you're differentiating is the thing up here. Okay, so here's a couple examples of takings of stuff with involving that. So if this is g of x, g prime of x is the derivative of the integral from 0 to x root 1 plus t squared dt. That rule we just said, that we just had, said that x gets plugged in for t. So this is root 1 plus x squared. That's it. Like, no joke, I swear, that is it. So g prime of x is equal to that thing. So, okay. Because remember how I said before we had g prime of x was equal to the derivative of the integral from 0 to x f of t dt is just equal to f of x, right? And I said 0 there, I meant to say A. This is true for actually any number. And I'll have a second way to explain that to you in just a moment, but that's, and now a couple of things this does depend on. It does matter that the thing you're differentiating goes from A to X. So like look at part B. What's the slight issue with that one as it is? It goes from X to 5. So can you change it around before you take the derivative so that it goes from number to X?
Negative.
Negative, yep. So negative 5 to X tan t squared dt. So then g prime of X is the derivative of negative integral 5 to X tan t squared dt. And so what will that be? Negative tan x squared. That's it. Okay, so first slight thing that could kind of go icky is that that upper bound could be an x. That might be a problem. Or could be, you could have them flip-flopped. Now the second thing that this does depend on is that in these functions, this is where the variable goes. And if the variable is anything other than x, you have to use the chain rule. So for example, this guy has a chain rule. So g prime of x is the derivative of the integral from 1x to the 4th secant t dt. So this derivative rule just says that the upper bound, that's the variable, gets plugged in for the dummy variable. So this becomes secant of x to the 4th. But because this is not just x, you got to multiply by the derivative of x to the 4th. That's the chain rule. So 4x to the 3rd. And that's a bit tricky, but you got to think like, okay, well with functions, I use the chain rule if the thing that's plugged in is something other than x. If it was like a, well, if there was, we multiply by the derivative of whatever that thing is, right?
So if it was, like natural or ln, you'd get 1 over x.
You'd first plug in ln x for t and then multiply by 1 over x. Yep. Okay, this one. So this has the same problem as part B above, right? So first thing you must do is negative. So g prime of x will be the derivative of negative integral 2 to 2x plus 1 root t dt. Negative. So what gets plugged in for the t? Nope. What gets plugged in for t is whatever's up there. Root 2x plus 1. And because the thing you plugged in was an x, you've got to multiply by its derivative, which is 2. There you go. There's the derivative. Oh, tricky grossness. Okay, one more that's super gross. Ready for super gross? And then we'll skip example 5, and because example 5 is in your book, and it's really not very hard. Why is this one super gross? Yeah, every single other one we've had, there's been one that's a number and one that's an x, right? And the rule does depend on that. So here's how you fix it. You take your g function, and you break it up into the integral from tangent to some number. I just always pick 0. It doesn't matter what number you pick.
And you have to flip it.
Yep. Plus the integral from 0 to x squared. And that's that property where we said, okay, we can find the area from lower bound to some number plus some number to upper bound. We can break it up into 2 pieces this way. It doesn't matter what number you choose. You pick 1, 7, 5, 11, whatever. And then now, one of them is still a little bit problematic. Which one? The first one. And to make it right, you have to flip it. Oh, that should be to tangent. Plus 0 to x squared over root 2 plus t. So g prime will equal.
Did you make an art sign of that? Or is it too hard?
Nope, you don't. The thing that's, everybody gets weirded out by this is you don't do anything with the thing inside the integral.
Oh, yeah,
Or you do nothing with it. All you do is plug in the bound. So this first one, you'll plug in what for t to the fourth? What goes in for t? Tan x would be tan to the fourth x. And because your thing you plugged in was not just x multiplied by its derivative, which is secant squared x, right? The next one, what gets plugged in for t?
X squared.
Uh-huh. Multiply by the derivative of the x squared, which is
2x.
And so final, slight simplify, negative secant squared x over root 2 plus tan to the fourth x plus 2x over the root of 2 plus x to the eighth. Those exponents multiply, right? No common denominator, nothing else simplifying, just that's it, that's great, it's all. And the kicker is, and the thing that students always mess up, and we'll see if you guys can not be like them, you don't do anything with that function. Other than this derivative rule says plug the variable in, multiply by its derivative, that's it. Okay, I know it's weird, super weird. So here is the part, we're going to example 5 because it's in your book, you can look at it there. So this is called this is the second part of the fundamental theorem, but it is definitely the part you use the most often. So this says that to find the area under a curve from A to B, the thing you do is you find an antiderivative of your function, lowercase f, and you plug the upper bound into that antiderivative, and you plug the lower bound into the antiderivative, and you subtract the two, and that gives you the signed area. That's how you do it. You don't have to do the whole nasty boxes thing. It doesn't have to be a semicircle or a rectangle or a triangle for you to find the area. You take the antiderivative, plug in the the upper number, plug in the smaller number, and that gives you the area under the curve. So we can actually, this one I'll actually show you why it's true, and then we'll do a couple. So we know that this weird g of x function, integral from a to x f of t dt, is an antiderivative of f since g prime of x equals f of x. That's what it means to be an antiderivative, right? You're an antiderivative of a function if when you differentiate your antiderivative, you get back the original function. Okay. And then we're going to say that any other antiderivative, capital F of x, will equal this g of x function plus some constant. You buy that? That's how antiderivatives can be different, right? They could be like the antiderivative of x squared, one is x cubed, and one is x cubed plus 3. They're different by some constant. Who knows what it is? Okay, so start with this. Then we're going to do capital F of B minus capital F of A. And we're going to show that that equals the left side. So that's going to equal g of B plus the constant c minus g of A plus the constant c. That's what it, because how f of x and g of x are related. first thing, what happens to the C's?
They go out.
They go away, they're just gone. This is just G of B minus G of A. Okay, next thing, take your G function. What is G of B equal to? If you plug B into that thing, what do you get? Integral from A to B, because you input B, and B gets put into that upper spot. How about G of A? That one is 0, Rachel, because you integrate from A to A, f of t. Oh, it says f of t, sorry. F of t dt. So the second piece is 0, right? So we just have the integral from A to B, f of t dt. The second one is A to A, right?
Is it always A day?
Well, that's what it means to do G of A, doesn't it? So yeah, it is always A to A. So that's the technical proof of why that works. It's weird. I mean, like, I get that it's strange.
Makes sense, I just couldn't tell if that was an
Oh yeah, that was an A, yep. Okay, so the point is to find area under curve, you find antiderivative, input first value minus input second value. Now, the one thing that you have to be careful about is that there was an assumption that your function was continuous. And if your function isn't continuous, this doesn't apply. You can't use this.
Jump thing.
If it's a jump thing, you can break it up into pieces and deal with it. But most of the discontinuities you're going to see are going to be things that are infinite discontinuities, like asymptotes and stuff. Okay. So the way to find the area under the x cubed curve from 1 to -2 is to find an antiderivative of x cubed. So let's just do 1/4 x to the 4th plus c. I'll put a c there this time, and then I'll discuss why we're never going to put a c there again, okay? And the way you say, like, plug in 1 and plug in -2 is you draw a straight line and put the 1 and 2 on it. It tells you you're going to input 1 and you're going to input -2. So when I input 1, I have a quarter plus c minus input -2, and I get 16 quarters plus c. What happens to the c's?
Goes away.
So the c's are going to cancel every time. I'm never going to put plus c again,
Okay.
okay? And this will be a quarter minus 16 quarters is,
-15 quarters.
yep. And that tells you what the signed area under the x cubed curve is from -2 to 1. And does it make sense that it's negative? So x cubed looks like this, right? And if you go from -2 to 1, more of the curve is going to be below the x-axis than above it, right? So that should be a negative answer, yes? But you get how that worked? Find an antiderivative, plug in the upper bound, minus plug in that lower bound. That's the area under the curve. Sign. Which is why we did antiderivatives in section 4.9. Yeah, go ahead.
No, I was just thinking, if the curve was the other way, which area you were looking at?
What do you mean by the other way?
If it was down this way.
Then you'd be looking at negative x cubed. I'm not sure what you mean.
No, it's good.
Okay, so what's an antiderivative of 1 plus 3y minus y squared?
3 is -2.
Okay, what's the antiderivative of 1?
X.
Oh, in this case, it actually has to be y, but yes. Okay, how about 3y? What's the antiderivative of 3y? 3 halves y squared. And how about the antiderivative of y squared? Great. And then you're going to evaluate that from 0 to 4. Means first take that thing and plug in 4, and then take away what you get when you plug in 0. So first plugging in 4, we get 4 plus 3 halves times 16 minus 1/3 times 64 plugging 0 into functions won't always give you 0, but in this case, it does, right?
As long as it's not a constant, right?
And well, or a cosine or an e,
Oh.
right? So you gotta be careful about functions of yeah, but if there was a constant, then yes, yeah, it'd be the same thing. So it'll be 4 plus, ooh, I think 28, do you agree? Because you can do 16 divided by 2 is 8. No, shouldn't agree. I lied. 24, thanks.
Half 48.
I was just adding the 4 already. Okay, and then minus 64 thirds. So 28 minus 64 thirds. Multiply him by 3 over 3. 60. I'm pretty sure that's 84 thirds.
Can you keep the word for that?
I think this time you can, because it's 60 plus 24. So that answer is what? Mm-hmm. Which means that overall, if you were to graph this 1 plus 3y minus y squared, there's more in, I hate that they use y because it makes you think it's sideways when it really doesn't have to be. There's more above than below, more positive area than negative area. So really, it's just section 4(9) over, right? And actually plugging in numbers. So what's the antiderivative of 3 over x? Does the 3 matter? Just a constant. What's the antiderivative of 1 over x? Natural log. Technically, you need absolute value bars there. 2 to 5. So that becomes 3 ln 5 minus 3 ln 2, or 3 times ln 5 minus ln 2. Can you write that as 1 natural log?
Divided by 2.
Mm-hmm. Great. I won't make you do that, but, you know, it's just a possibility that it could happen. Okay. How about this one? Antiderivative of cosine.
Negative sign.
Wait, I think it's just sine. Yeah, it's okay. I'd say I know it's the other trig function, then just check by doing a derivative, right? That's how I figure it. I would say, okay, sine's derivative is cosine, so it's positive sine. That's how I do it. I don't know if that's perfect, but that's what I do. 0 to pi halves. So that will equal sine of pi halves minus sine of 0, which is uno, right? 1 minus 0. Sine of 0 is 0. Yeah. It's less confusing than the part that, and I can actually explain why that other part is true using this. So I'll do that at the end. Do you like this part better than the previous part? Antiderivative of x cube rooted. So that's x to the what power?
1/3.
Oh, yeah, first it's 1/3, but when you antidifferentiate, you get x to the 4/3. And what do you need in front? 3/4. Great. And I think I gave you numbers that you can actually work out. So 3/4, 8 to the 4/3, minus 3/4 times 1 to the 4/3. Okay, so how do you work out 8 to the 4/3? What does the third do? Cube root 8, and then the 4th, right? You could also 4th power and then cube root, but that would be a bad decision. So that is 16. So I've got 3/4 times, I think it's 16.
Well, after you.
Oh, after I, do you see what I'm saying? Because 1 to the 3/4 or 4/3 is just 1, right? So, here's you can do this, you could say 48 over 4 minus 3 over 4, which would be 45/4, right?
Couldn't you?
You could take out the 3/4 and say 16 minus 1, which is 15, and 15 times 3 is 45.
Yeah, I was doing 16 times 3.
Oh, that works too. That'd be fine as well. Then you just have to get a common denominator anyway, so yeah.
Oh,
But either way. Is that all right? Okay. You would get 11.25, I think.
16 divided by 4 times 3.
No, for the final answer. 16 divided by 4 is 4. 4 times 3 is 12. 12 minus 3/4 is 11 1/4, isn't it? Or, 11.25. Don't give WebAssign this answer. It will tell you that you're wrong. Because it doesn't know if it's 11 plus 1/4, which is what it really is, or 11 times 1/4, which is what it looks like, right? It's bad. It's really bad notation that is just not fixed in the school system. You can give it 45 quarters. You can give it 11.25. Okay, that's.
Take if it was like 11 plus 1/4.
I don't know. That's a good question. You can try, but I'm not sure. Probably not. I suspect not, but I mean, I don't know. I haven't tried. Okay. Cosine of theta d theta. So what's the, okay, so antiderivative of cosine theta. So sine theta, is that right? Okay. Pi to 2 pi. So what's sine of 2 pi?
0.
What's sine of pi? And you can just ask yourself, do you believe that? So the cosine curve does that kind of business, right? And so do you believe that the area, based on the picture, the area from pi to 2 pi is indeed going to be 0? Yeah, they do appear to be the same shape and then they cancel out, right? So if you get that, don't freak out. It's possible. Okay?
Isn't that cosine?
Yeah, but that's what you're finding. You're finding the area under cosine. So finding the area under cosine involves using its antiderivative, but the function you would graph would be the original one. Yep, good question though.
What's the in circle? That's what I was looking at.
Oh, but the graph of cosine is not the unit circle. All right, what's the antiderivative of cosecant x, cotangent x? Negative cosecant x. So we'll have negative cosecant of pi halves. Is it okay if I say plus cosecant of pi 6? So why did I say plus? Yeah, minus a negative. So cosecant is 1 over which trig function? And so use your unit circle to figure out what those are. So what is sine at pi halves? So negative 1. How about pi 6? What's this? So 1 divided by a half, same as, it's 2, yep. So negative 1 plus 2 will give us 1. Yay. Was there any product rule for antiderivatives? Was there any quotient rule for antiderivatives? Okay, so quit trying to make one that's just bad. So if you see a product or a quotient, your options are to multiply it or divide it before you take the antiderivative. So can you multiply this together before finding the antiderivative? Yes. So 0 to 1, that becomes 3x, and x to what power? What's x times root x? X to the 3 over 2, because the exponents have to add. 1 plus 1/2 makes 3/2, right? Okay, now can you antiderivative? So what's the antiderivative of 3x?
3 over 2 times x to the
Great, 3 over 2 times x to the second, very good. And how about x to the 3/2?
x to the 5/2, so n times 2.
2 over 5, great. Okay, and plugging in 1 is nice and easy, isn't it?
3/2.
Yeah, you have to have 3/2 plus 2/5, right? And then the plugging in 0 does give you 0, right? So just get a common denominator, 15/10, right? Plus 4/10. Is 19/10, right? Okay, great.
Just be 3/2 plus 0.
But you plug the 1 into both the 3/2 x squared and the 2/5 x to the 5/2.
Oh.
Right? Okay. Okay, there also be no quote rule for antiderivatives. Don't make one up, it's gonna be wrong. Okay, so your option here is to break this up into two pieces and do the division. So 1 to 3 x cubed over x to the 4th plus 3x to the 6th over x to the 4th. Or you can bring the negative up and add exponents, but that seems to not work so well, so I'm gonna do it this way. So how does x to the 3rd over x to the 4th reduce? How about 3x to the 6th over x to the 4th?
3x squared.
Great. If you see a quotient, you have to do this. This is the only option. All right, now you take your antiderivative. It's the antiderivative of 1 over x.
Natural log of x.
Officially with absolute value bars, but yes. What's the antiderivative of x to the 3rd, x to the 2nd? I just told you. X cubed. Sorry, I ruined the surprise. Is that okay? All right, first input 3. ln 3 plus 27, right? Minus ln 1 plus 1. You gotta know what natural log of 1 is, but you also allegedly passed pre-calculus, so 0. So this is ln of 3 plus 26. Awesome. Is that all right? Most of this is just antiderivative recognition, right? So if you know section 4.9, this is not that bad. Okay. This guy, remember how constants can get factored out?
9/10x.
So it becomes 9 integral 0 to 1, 1 over 1 plus x squared. So very simple function. Whose derivative is 1 over 1 plus x squared? Arctan. So 9 arctan x from 0 to 1. So you have 9 arctan 1. Oh, look at, I can make you find arctan without asking you to find arctan, like explicitly. You see what I'm saying? Like, on your final exam, I can make you do this, which also tests, do you know how to find arctan of 1?
It's just dirty.
It's just mean. It's so mean of me. So when does tangent equal 1? The root 2 over 2 isn't the answer. The answer is the angle. Pi over 4. And well, officially, pi quarters for when is tangent 1, you have to use negative pi quarters. Remember how that was for sine and cosine, for arcsine and arctan, it was negative pi halves to pi halves, right? That was this half in that direction and that direction. And arc cosine was 0 to pi.
Wouldn't the bottom negative pi over 4 that would be a negative?
That would be if I'd asked you to find arctan of negative 1. Yeah. What is arctan of 0? When is tangent 0? 0. So the answer is 9 pi quarters for this one. Oh man, oh man. This one's only a little bit tricky. Antiderivative of 5 to the x. So obviously it's going to contain a 5 to the x, right? I think. Now the derivative of 5 to the x is ln 5 times 5 to the x, right?
So it's going to be 1 over ln 5?
Over ln 5. Or 1 over ln 5 is the same thing, right? what's the antiderivative of x to the fifth? 1/6 x to the sixth. Awesome. Okay, so that's going to be 5 squared over ln 5 plus 2 to the 6th over 6 minus 5 to the 0 over ln 5 plus 0 to the 6th over 6. Okay, so that's 25 over natural log 5. What is 2 to the 6th?
32.
That's 2 to the 5th. 64. Gesundheit. What is 5 to the 0? 1. So can you simplify that anymore? 24 over ln 5. And I mean, you should reduce your fractions because like you're in calculus and you can do that now. How does 64/6 reduce? 30, yeah. Okay. Woo, yay. Okay, one more trig. What function is the antiderivative of 1 over root 1 minus x squared? Arcsine. Okay. So arcsine root 2 over 2 minus arcsine 1/2. So when is the sine root 2 over 2? At what angle? Pi fourths. When is the sine 1/2? Is it pi 6 or pi thirds? Pi 6, very good. So that becomes 6 pi over 24 minus 4 pi over 24, getting a common denominator, right? I guess you could have also done 12 for a common denominator. That would have been smarter, but I just wasn't thinking. So 2 pi over 12 or over 24. Oh my gosh, I really wasn't thinking. Obviously, pi over 12. I left my brain someplace this morning. So in a nutshell, that's kind of what's going on with this lesson. This shouldn't be super difficult, right? Okay, last example, and then I'll go back and explain that other thing one different way to make it make a little bit more sense, I believe. What's wrong with this calculation? And the error isn't obvious. So the person, whoever did this calculation, they found the antiderivative correctly, and they did the arithmetic correctly, right? At least you buy that, right? There's a problem with the original step from here to here, that this step is wrong. And the reason it's wrong is that the function f of x equals 1 over x squared is not something on the interval from -1 to 3. Fill in the something. What's wrong with that function?
It's not continuous.
It's not continuous. And specifically, it has a vertical asymptote at x equals 0. So you should actually kind of in every question be asking yourself, is f of x continuous on the interval from a to b that you're given, like yes or no? And if it's not, the integral won't exist. Those things might be mixed up in the homework questions. Like they might say, oh, find the integral from, I don't know, 2 to 4 of 1 over x minus 3, for example. Maybe they'll try to do something like that, which you don't actually know how to do yet, but 3 is an issue, right? And 3 is between 2 and 4. You'll learn a way in calculus 2 to figure out the value of integrals like that if they exist in the first place.
if we get something like this, then it's just wrong.
You just say does not exist. For, at this stage in your like mathematical development, does not exist is all you say. Okay.
I mean, if it's shooting up, if the function's shooting up to infinity or down to negative infinity, I mean, wouldn't the area be infinity?
Depends on how fast it goes to infinity. So, and yeah, so here's kind of a crazy question related. You can actually find the integral from 1 to infinity of 1 over x squared. Like the area under the curve, 1 over x squared, from 1 to infinity. That actually is a finite number. Like it equals, it's like, I think it's 1 over, it might even just be 1. I'm pretty sure that this equals 1, okay? But if I give you 1 to the infinity 1 over x, which is a little bit above that curve, right? This will actually be infinite. So that answers your question about asymptotes, is that it depends on how quickly the function goes to the asymptote. But the area might be fine. Infinity is those strange, weird stuff, okay? That's calculus 2, chapter 7, section 8. Okay, that's if you're taking calculus 2, but you'll do, and it's actually not very difficult to do these things. Okay, but back to this class. If I gave you the function g of x, just write this in the back page, you got some blank space, this will help. G of x is the integral from 0 to x, we'll say sine of t dt. The rule we had said g prime of x, or the derivative of this thing, is the thing that weirds you out, because all you do is plug in what for t? X, and that's just equal to sine of x. That's the rule, right? Here is another longer way, okay? Pretend we didn't know that rule for just a second. G prime of x is the derivative of the integral 0 to x sine t dt, okay? Pretend we don't know that it's going to be sine x, just for a second. Can you do this integral doing the stuff that we just did? As in take the antiderivative, first plug in x, then plug in 0? Do you see what I mean by that? Okay, so did I do this derivative operation yet? If I'm working out this way, so then I'm going to leave that d over dx, or that signifies I still have to do the derivative. But I'm going to evaluate that integral by saying the antiderivative of sine is negative cosine t, right? And the things I plug in are 0 and x. Is everyone okay with what happened there? Okay, so then I have the derivative of negative cosine x plus cosine 0, which is 1. Now can you take the derivative? What's the derivative of negative cosine x? So, well, negative sine x, which is just sine. What's the derivative of cosine of 0? 0, which gives us back sine. First you anti-differentiate, plug in x, then you differentiate, which undoes what you just did. You see what I'm saying? Look at this and look at the answer. What changed? The t became an x, right? Let me change it a little bit to also explain the chain rule, okay? So what if I made this g prime of x, the derivative, let's say, make it 0 to x cubed, okay? Sine t dt. Just, all I changed was the x to x cubed, right? So using the rule that we know, g prime will equal sine of x cubed times 3x squared, right? That's from the rule we learned before. Let's just do it the long way and I'll show you why. So if you anti-differentiate sine, you get negative cosine again, right? By that? Okay. So then you plug in negative x cubed. And plus cosine 0. What rule do you use when you take the derivative of that? The chain rule. So that becomes negative sine of x cubed times 3x to the second, which gives us back what the other rule said we would get, right? This also explains why this number doesn't matter what it is. Like if that had been like 2, this would have been cosine of 2. Cosine 2's derivative was 0, right? Also, if these things were flip-flopped, you'd have the 0 first and the function second, right? Which would mean the negative would come in front of the function. So the thing is that you're just supposed to know this pattern, and doing it this long way depends on being able to find an antiderivative in the first place. See what I'm saying? For lots of functions, you won't even be able to anti-differentiate the craziness. It just won't be something you know, recognize or know how to do. Okay, so that's it. Nice job. Yay. So for those of you who walked in late, just